So, good afternoon, everybody. You have reached the room for session C06, Renewable Energy Production. I am Cheryl Spencer. I'm the chair of this session. I'm the secretary-treasurer of the Forum on Physics and Society. This session actually was organized and developed and thought about by a different member of our committee, Eliane Lesner, who was not able to be here. So I give her thanks. I'm just a stand-in chair. Okay. So we will have 3 talks, and each speaker will come up. They will have 30 minutes to speak, and then there'll be a 5-minute period where you can ask your questions. You will all go to that mic there in the middle corridor. These sessions are being recorded for their voice and their slides. So that's why we need the questions to be asked into that mic. And I think those are all the instructions. I can also tell you that we are recruiting new members of the forum. I have the ability to scan the QR code on your badge if you want to join the forum, and you will automatically get joined at no cost. And we'll do that at the very end. I can scan your badges. Okay, so now let me introduce our first speaker. Jo Rand is an energy policy researcher in the Electricity Markets and Policy Department at Lawrence Berkeley National Lab. Jo conducts research and analysis on renewable energy, including renewable energy policy, cost, market analyses, spatial data analyses, and research related to social impacts, grid interconnection, and deployment barriers of renewable energy. Jo has been awarded an Excellence Award from the Energy Systems Integration Group, the Switzer Environmental Fellowship, a research fellowship from the Hydro Research Foundation, and the Novus Ventus Award from the US Department of Energy's Wind Power Program. His research has been widely reported on in the press, including the New York Times, NPR, the Washington Post, the Wall Street Journal, CNBC, and even last week tonight with John Oliver. Jo holds a master's degree in engineering and resources from the University of California, Berkeley, and a bachelor's degree in environmental studies from Macalester College. So let us welcome him as he speaks to us about opportunities and barriers to the widespread deployment of renewable energy in the US. Thank you, Jo.
Okay, well, thanks for the introduction, Cheryl, and thanks to you all for having me, for the invitation. So we have 3 speakers today, and I wanted to start by giving kind of what's going to be a high-level overview of the status of renewable energy deployment in the United States and the challenges to achieving, really aggressive targets and goals that we have to meet decarbonization goals and mitigate the worst effects of climate change. So really, I guess my talk should say achieving 100% clean electricity by 2035 in the United States. Of course, we're just one of many economies that are working on this challenge. So just a quick overview of what I plan to speak about today. Again, this really is framed around the vision of achieving a zero-carbon electric sector by 2035. We have separate goals to reach a zero-carbon full economy by 2050. I'm going to be focused on the electric sector today. So really, first, I'll give an overview of this vision. What does that mean to reach a zero-carbon electric sector by 2035, and what do the pathways to get there look like? And then what's the current status? Where are we now along those pathways, and what is it going to take to get there? Next, I'll get into kind of a future outlook. So kind of moving from where we are today to, what do the next 12 years look like? What can we see in the data that inform us of how we might kind of move along that pathway to zero carbon? And then kind of the last section, I'm going to be really talking about challenges and barriers to meeting these goals. And I have a few different topics I'll talk about there. And then I wanted to end on a kind of more optimistic or hopeful note. So I have one slide that's really focused on solutions. So there are indeed a number of challenges and barriers I'll speak to today, but I wanted to also highlight some things we can do today to enable us to overcome those barriers and reach this goal. Okay, so starting with this vision, pointing towards 2035. and reaching a zero carbon electric sector. So when we look all the way out to 2035, a lot of the studies are showing us that we need to deploy 1,500 to 2,000 gigawatts of combined wind, solar, and battery storage capacity. That's a whole lot. I assume as physicists in the room, that these numbers and the watts, the units of power make sense to you all, but 2,000 gigawatts represents a whole lot more than our current installed US power plant fleet, just to put that in perspective. The chart that I'm showing, let's see if I can go back here. The chart that I'm showing here on the y-axis shows the installed capacity of these technologies. And of course, the x-axis is just a timeline from 2010 looking out to 2035. And the red vertical bar just represents where we are today. Not sure what that beeping is. Okay, great. So what I want to emphasize is that I conveniently placed this red line and kind of this timeline really halfway along that timeline. So if you look at these lines, these represent installed capacity of wind in green, solar in yellow, and battery storage in blue. So that's where we are today and kind of the historical look. And then these pathways represent different studies from the National Renewable Energy Lab, Princeton University, UC Berkeley, and a White House report, basically laying out different pathways to reach, again, a zero carbon electric sector by 2035. So what I want to emphasize is, along this timeline, we're roughly halfway, and we've deployed roughly 10 to 15% of the wind and solar that we need to reach that target. So we have a long way to go. I don't want us to get pessimistic about that because we're actually doing pretty well if you look at kind of the growth rates of these technologies, and I'll get to that in a few minutes. Okay, so now let's lay out the vision of, let's see, I think I just went backwards. Okay, here we go. So when I showed that slide and I talked about where we are now and where we need to get, which is a lot further than where we are now, again, we're 10 to 15% of the way there. I want to ask just an informal poll of this audience. What do you all think are kind of the main barriers to us achieving this goal? Is it economic, like the cost of wind and solar and batteries is too high, or the market value is too low, it's hard to get financing? Is it technical? Are there, engineering challenges are kind of the main barrier? Or is it more kind of siting of these power plants and social factors, social opposition, land use conflicts, ecological impacts of these plants? Is it transmission issues? So, our aging transmission infrastructure in the United States and connecting new power plants to this grid? Or is it more of a policy problem, like lacking a kind of coordinated all-of-government approach to solving this issue? Trade wars, tariffs, and supply chain issues. So let's do really quick. Just raise your hand if you think it's economic issues. All right, I'm seeing a few. It's okay if you want to vote for more than one. I'll allow that. It's a little bit weird, but I'll allow it. Okay, technical. Who thinks it's kind of technical issues? The technologies are not mature. Managing the variable output is too challenging. I'm seeing like a couple sort of maybe hands. Siting, social, environmental. Okay, a few more. These are big issues. Transmission connection. Okay, this one's a little more popular. And then policy. Okay, great. A lot of people think policy and some enthusiastic hands. Yeah, sure, I'll throw that in there too, yep. So yeah, and I'm gonna stress, of course, it's all of these things. But in my talk today, I know this is a physics audience, you guys are very technical, engineering focused. There are technical and engineering issues that we need to address. But I'm going to focus my talk on things that maybe we focus a little bit less on, siting, social, environmental, and transmission connection. I'll spend a lot of time talking about transmission. And what I want to emphasize through my talk is that, I think historically, as we've gone along this pathway, and gotten to where we are now today, I think historically, the things we focused on were improving the economics of wind and solar, and addressing kind of these technical and engineering questions. But increasingly, I would argue that the barriers to widespread deployment of renewable energy are social, institutional, and regulatory in nature, and less so economic and technical. So I'll get to that in a few slides. It is all of the above, but I think we need to focus on other things. So now I'm transitioning into the status, where we are now. So this is a chart showing the installed capacity of wind, solar, and batteries from 2000 through 2022. I'm borrowing this from the American Clean Power Association, but they just keep really good records and data of this stuff, so it's nice to use their chart. We have currently 227 gigawatts of wind, solar, and storage installed in the US. Again, remember, we're aiming to 1,500 or 2,000 gigawatts or so. Wind energy alone represents roughly 10% of our US electricity generation, and utilities represents about 3%. Distributed kind of rooftop solar represents another percent or two. And then we have about 9 gigawatts of battery installed and you can see how many gigawatts were installed just in 2022. I don't know if my pointer's working, but yeah, so 9 gigawatts of wind, 13 gigawatts of solar, and 4 gigawatts of battery. So we're doing pretty well. Again, to meet the target, we do need to accelerate. The other thing I want to emphasize is that, renewables are on a really strong growth trajectory. You can see that here in the green line. So is fossil gas. So, that's something we need to think about and eventually really address. But the good news is we see coal on a precipitous decline. And for the first year in 2022, renewables actually generated more electricity than coal and nuclear. And when we look at just breaking down that green line of renewables, wind energy alone generates more than half of our renewable electricity in the United States currently, but we see a really strong growth trajectory from utility scale solar. And again, I should mention I'm borrowing these figures from Canary Media, who generated these nice charts based on data from the Energy Information Administration. Sorry. All right, here's a really busy chart, so I'm going to take a minute to explain it. But really the point here is we're asking the question, why is demand for clean electricity surging? And I'm going to answer this in a few different ways, but number one, I'm going to talk about economics. So this chart, on the y-axis, I'm showing the levelized price of PPAs, which is power purchase agreements, so the offtake or agreements to buy electricity from renewable power plants. And then, of course, again, the x-axis is a timeline from 2009 through 2022. And what you can see really clearly is, the average power purchase agreement for solar in orange and wind in blue on a pretty steep decreasing curve over this timeline. The circles just represent different power plants or actual power purchase agreements, and the size of the bubble is based on the size of the power plant. Really just focus on the trend here. We see really rapid declines of solar and wind, and then the black bars are representing kind of the levelized average cost of operating an existing natural gas power plant in the United States. So amazingly, back in around 2011, 2012, we saw wind power purchase agreements at prices lower than the cost of operating a natural gas power plant, and they've remained below. And then solar also recently decreased to below the average cost of operating a gas power plant. So just from a simple economic standpoint, it makes sense to be deploying more wind and solar. The other driver, of course, is policy. So what I'm showing in this map are what's known as renewable portfolio standards, which are state-level requirements to procure a certain amount of electricity from renewables by a certain year. We have renewable portfolio standards now in 30 states and Washington, D.C. 12 of those states have 100% clean electricity standards by 2050 or earlier, meaning they have to procure 100% of their electricity in state from renewable sources. Of course, we have these federal targets. The Biden administration, this is kind of what I'm framing my talk around today, is hitting zero carbon electric sector by 2035. We have tax incentives under the Inflation Reduction Act. And then we have utilities. So even if you're not in a state with a renewable portfolio standard, you're most likely served by a utility that has a decarbonization commitment. 84% of US customer accounts are currently served by utilities that have some level of decarbonization commitment. So again, this is just another driver of demand for renewable electricity. And the last one I'll mention is kind of this idea of social and environmental responsibility. A big driver now is corporate procurement of renewable electricity. So we have big corporations like Google and Facebook, I guess I should say Meta, wanting to buy clean electricity to power their operations. Back in 2013, these corporate power purchase agreements represented about 2% of announced new, offtake agreements for renewable power. And as of 2022, they represented 59% of announced agreements. So these big corporations that are buying renewable power has become a major driver of demand. All right, so with all that, let's look at the outlook. What's in the pipeline? So the outlook, first I'm going to talk again about cost. We recently did an expert elicitation survey of 140 global wind energy experts to ask them about their anticipation of future costs for wind energy. And those expectations are shown in this chart with the levelized cost of wind energy, again on the y-axis, and time from 2020 out to 2050 along the x-axis. You can see offshore wind energy declining a little bit, about 17% by 2035, and fixed bottom offshore and floating offshore wind energy declining rapidly in that time frame. So, closer to 35% cost decline by 2035. And I want to emphasize that similar or greater cost reductions are widely anticipated for solar and storage, though I don't have time to get into that today. So speaking of the pipeline, look, we saw all this growing demand. We've seen declining cost trends over time and expectations for even further cost declines out into the future. So how do we look at what people actually want to build? What are the power plants that are in the pipeline? Well, one way that we do that is that our team at Berkeley Lab collects data from what are known as interconnection queues. Now, these are the lists of power plants that have applied to connect to the grid system. They're not built yet. It basically means that there are project developers, wind and solar project developers that want to build these projects, and they've submitted an application to the electric grid operator to try to connect. What we're finding is we have over 2,000 gigawatts of generation and storage capacity in these interconnection queues across the United States seeking to connect to our grid system. It's just a remarkable number. That's spread widely across the United States. And as you can see from these charts, the vast majority of that is wind in green, solar in yellow, and storage in blue. Again, you'll also notice the growth of those interconnection queues, the growth of capacity that's seeking to connect to the grid from 2014 to 2022. I think it's been something like a 6-fold increase in that time frame. Just a deeper dive into these interconnection queues. When we break it down by technology or the type of power plant that's trying to connect to the grid, in the United States alone, we have about 950 gigawatts of solar, 680 gigawatts of storage, and 300 gigawatts of wind energy that are across the United States trying to connect to the grid. Again, these haven't been built yet. They may be at various stages along the development process, but this is kind of what developers are wanting to build right now. The other trend I want to point out here is look what's happening with gas. So from 2014 to 2022, we see a decline in developers' applications to connect new gas power plants. And then you don't really see much of anything else. That's also pretty remarkable. So I think nuclear, we might have 5 gigawatts in the queue, coal, essentially nothing, and then a smattering of other types of power plants. But really, everyone's wanting to build solar, storage, and wind right now. One more focus slide on these interconnection queues. The other thing I want to point out is the magnitude of what's in the interconnection queues compared to our installed capacity, the entire US power plant fleet. The whole US power plant fleet is about 1,250 gigawatts, and you can see what that's made up of here in this chart. So, a whole lot of natural gas capacity, coal, nuclear, hydro, and yeah, like I showed earlier, some wind and solar. Compare that to what's in the queue, and first of all, just the sheer magnitude, the size of that bar, there's a remarkable difference. But secondly, the makeup of that bar. What we see, again, in the queue, it's all solar, wind, and storage with a tiny bit of gas. And the last thing to note on this chart is just to compare that to how things looked in 2010, so 12, 13 years ago. At that time, the interconnection queues represented just about 50% of the installed capacity. And the makeup of those queues was just fundamentally different than what it is now. So we are in the midst of a very rapid energy transition. You can see that in these data. And in fact, I'm going to quote Amory Lovins here, who said, "The energy revolution has already happened. Sorry if you missed it." And I think that's really shown in these data. Okay, so now I'm going to spend some time just checking the time here. Now I want to talk about the challenges. So, it's amazing to look at this chart and think, wow, we've already got enough capacity in the queue to meet that 2035 goal. Yeah, that's true, but there are a lot of things that are preventing us from getting there. So I'm going to spend a little bit of time talking about that. What's delaying or derailing clean energy projects today? Again, here, I'm going to steal a chart from someone else. This was produced by Level 10 Energy from a survey they did in 2021 that asked wind and solar energy project developers, what are the main barriers to achieving a goal of 40% solar in the United States by 2035? And this is coming straight from the developers of these projects. the vast majority, or by far the leading challenge or barrier that they indicated, I don't know if you can read that in the back, it says interconnection, timelines, and costs. So again, this is what I've been talking about a lot today. Connecting new power plants to the electric grid, the timeline, the amount of time it takes to do that, and the cost that developers have to pay to upgrade the grid in order to connect their project. This is a major prohibitive barrier to actually connecting these projects. And then the second one, I'll also talk about this today, is permitting challenges. So getting your local siting authorization to actually get your project built in the local community where you want to build it. Of course, there are other issues. I think this supply chain one is a very big deal, and increasingly, with COVID and the tariffs that we're seeing on solar panels right now, there are definitely a lot of issues, but I'm going to focus mainly on these top two today. All right, so first, starting with talking about transmission and grid interconnection. Again, there's a lot going on in this chart, so I'll step through it slowly, but I just want to stress that the way that we connect power plants to the electric grid today was basically formulated in 2003. 20 years ago, we had a very different electric system than we do today. It was really designed around fewer, larger, more centralized power plants, i.e. coal and natural gas power plants. Like I just showed in the interconnection queues, the grid system of today and of the future is wildly different. So we do need to reform the way that our interconnection system works to accommodate this new reality. Unfortunately, when you build a new power plant, you can't just plug it into the grid like we plug in our phone to the outlet. It's a lot more complex. First, you submit the interconnection request. You conduct a series of interconnection studies, a feasibility study, system impact, and facility study. And those are really designed to determine what grid upgrades would be necessary in order to safely connect that new generation, safely and reliably. And then those studies also allocate the cost of those upgrades. So let's say I connect to a substation and I need a new transformer, or I need to upgrade the electric conductor in that local area in order to safely accommodate my new project. Typically, the developer of that project pays for those upgrades. So this adds to the cost of those projects, right? Now, I want to stress that process has been widely criticized because if we charge all of those costs to the developers, in many ways that's unfair because those upgrades to the transmission system bring broad social benefits. It's not just a private benefit to the developers of those projects. So one major reason we need to look into reforming that process. One last thing I'll highlight on this slide is that throughout this process, you can see these little red X's, and those are projects that withdraw. So entering the interconnection queue is not a guarantee that your project will be built. And I'll talk about this in a moment, but many projects end up withdrawing through this process, and those projects are canceled and never built. And the last thing I'll say, the study process culminates in what's called an interconnection agreement, which is basically a contract between the developer of that wind or solar storage project and the grid operator, or the owner of the transmission system. So I talked about projects withdrawing, right? When we looked at these data from the interconnection queues, we found that only 21% of the projects that had applied for grid interconnection prior to 2018 have been built as of the end of 2022. So we have very low completion rates for, that 2,000 gigawatts I showed in the queue. Is all of that going to be built? Unfortunately, no. We have, pretty low completion rates. 72% have been withdrawn, and 7% are still trying to get connected. And I want to stress that that completion rate is by number of projects. When we examined it by the capacity, the electric generating capacity of those projects, the completion rate is even lower at about 14%. And of course, there are regional differences. So California is really low. The Southeast and New York have really low completion rates. Texas has pretty high, relatively, and the Northeast too. The other problem is that it's taking longer and longer for projects to move through this interconnection process. So one of the ways we look at that, the chart on the left, I'm showing the duration of that interconnection study process. So from when you first submit your interconnection request, doing your feasibility, system impact, facility study, to signing an interconnection agreement, how long does that process take? And what we see is, these are just acronyms for various grid operating regions in the United States. Oops, let's see, going the wrong way here. The same regions that I showed on this map. Oh geez. Okay, so how long does it take? you can see in many of the major markets or grid operating regions across the United States, it now takes over 3 years just to complete that series of studies. This is not even including construction or getting your local permitting. Just to get the interconnection agreement, it can take over 3 years on average. And of course, you see wide distribution of that time. The chart on the right, I'm showing the timeline from the interconnection request to actually having an operational, functional, built power plant. And again, you can see that that duration on a pretty rapidly increasing trend, which is not really good for our decarbonization goals. Back in 2005, it would often take less than 2 years to go from your interconnection request to having an operational power plant. And now we're seeing the typical power plant taking 5 years to go from their interconnection request to coming online. I talked a little bit about these grid upgrade costs and how that's a major factor for developers withdrawing from the interconnection queues. So like I said, when you submit your interconnection request, do your studies, you're allocated a cost to upgrade the grid to connect your project. And what we're finding is, first of all, well, let me just back up really quick. We examined this across 3 cohorts, 3 different types of projects. So those are projects that are complete. That means they have completed that interconnection study process. We looked at active projects. They're still working their way through that interconnection study process. And then separately, we looked at withdrawn projects. So projects that started the interconnection study process and then ultimately withdrew. And what you see across all 3 cohorts is increasing costs that are assigned to these project developers from the prior period to the more recent period. So developers are facing higher costs now to interconnect their projects. But also, of course, and this is somewhat to be expected, you see much higher costs for withdrawn projects. So what this indicates is that when developers are assigned these really high costs to plug into the grid, they're just going to pull out. Their project is no longer economical. And when we looked at we compared these interconnection upgrade costs to what would be a normal or typical total capital expenditure for a wind or solar power plant. And in some cases, just connecting to the grid could account for 1/3 of what you'd expect your total project CapEx to be. So clearly, this is a major barrier. Related, but somewhat different, is upgrading the transmission system across the United States. Now, again, when we looked at all those net zero by 2035 studies, or I should say 100% clean electricity by 2035, they all require more transmission. Our transmission capacity in the United States, it's pretty much full, right? So we need to build more. That's really hard to do. Looking at 2020, these green lines basically represent where the transmission is and how much power they can move. And then looking ahead to 2035, this is kind of one of the scenarios. You just see a lot more green. That means more transmission. At the same time, when we look at how much transmission we've actually built in recent years, the trend is going the wrong direction, right? So we're seeing a decreasing amount of miles of new transmission lines completed each year. But this is, again, just a major problem. That's leading to these increased costs of grid interconnection because we don't have space on the transmission lines. So if you don't have space for more capacity, you have to upgrade that transmission line if you want to plug in your project. All right, I have a few more minutes here, so I'm going to talk about social impacts. Again, I know this is a very technical room probably, but I think it's important to note that there are real social barriers to not just the technical and engineering issues, but social issues that affect this as well. First thing I want to note is that to reach this 2035 goal, many, many more communities are going to be living in proximity to wind, solar, storage, and transmission. I mean, that's just a given. We have to build a lot more power plants. More people are going to live close to them. So to interpret this chart, on the x-axis, well, let me just say we have several different types of infrastructure, wind, solar, and transmission. And then along the x-axis, we have kind of the distance from those infrastructure projects. And then the y-axis is showing the millions of people that live in proximity to those projects. The gray lines represent basically where we are now. So how many millions of people live within 15 miles of a wind plant, for example. And then the colored yellow, orange, and red lines represent different scenarios to reach 2035. Suffice it to say, a lot more people are going to be living close. And I want to stress that a lot of research is telling us that solar and wind can be deployed more quickly and at lower cost if projects are structured to address the concerns and meet the needs of these hosting communities. Really important to pay attention to that. The other thing I want to stress is this is not just a NIMBY issue. Have you all heard the word NIMBY? Not in my backyard, right? I think a lot of times we say, oh, this is just a bunch of NIMBYs. They don't want wind projects near them affecting their view. Okay, there are visual impacts from wind energy, but I want to stress this, NIMBY, first of all, it's kind of pejorative. I think it puts opponents off. They're like, that's, doesn't explain my concerns. It doesn't help us from a research standpoint understand how to kind of work with communities and move beyond this opposition. But moreover, there are legitimate issues that we need to think about. So from the planning process, to how we develop wind and solar power plants, economic impact. So could a wind power facility in my community actually affect my residential property values? We need to understand that. There are sensory impacts, especially for wind. There could be visual, sound, or shadow flicker impacts. And just how we impact communities and their sense of place. Okay, I think I have 4 more minutes of the talk, because that was 25. The timer was for 25 minutes. Okay, we'll get there. Okay, so there are, like I said, negative socioeconomic impacts that we need to understand or compensate. Berkeley Lab, our team at Berkeley Lab has done a lot of research on this. Previously, we found no statistically significant relationship between wind turbines and residential property values, but we did find an impact with living within 500 feet of electricity transmission lines. All right, for my last slide, let me talk about solutions. So again, I focused a lot on kind of social impacts and transmission impacts. So first, we need to improve social outcomes for communities that are hosting this infrastructure. So how do we do that? Enhance the fairness and justice in this planning process, how we plan and develop and build power plants. Moving away from a decide, announce, defend model to consult, consider, modify, proceed. So working more with communities to build these projects. And then we need to distribute the benefits of these projects. So we can't just have third-party developers coming in and extracting all the benefits and profits. Of course, we need to reform that grid interconnection process that I talked about. We need more data transparency in that process. And we need to move away from just a line that serves the first come, first served to more of a first ready, first served approach. And I should stress that some of those activities are underway through reforms that are happening at the Federal Energy Regulatory Commission. And then finally, I can't put it any other way, we need to build transmission. I love this catchphrase, no transition without transmission. So we just need to do it. It's going to be hard, but we have to. So I'll stop there for questions. Thanks.
Okay, yes, speak into the mic, please.
Yeah, thank you so much. When one's thinking about carbon-free energy, even starting where we are today, there's hydro and there's nuclear, which are non-negligible, and which could also be non-negligible into the future. I'm curious why these scenarios don't include that, and if you're looking at the 1.5 to 2 trillion or gazillion, whatever the numbers were that you had at the beginning, those aren't included.
Yeah, great question. So a couple of things I'll note. So one of the charts I showed renewables just now surpassing nuclear. So nuclear does provide about 20% of our electricity in the United States right now. And I will say, I think it's really important to keep those plants operational to the extent that it's safe to do so. Why are we not forecasting, or why do these models not expect continued build out of hydro and nuclear, at the rate that we're building solar and wind? A couple things. One, it comes down to cost, right? So wind and solar now has become so much cheaper to build and deploy than nuclear. So I think it just from a standpoint of rapid and lowest cost, meeting this target at the fastest and lowest cost, it makes sense to do it with wind and solar. And then, I think the other thing I would say, I talked a lot about kind of social issues and acceptability of these technologies. Again, I just think frankly, it's a lot easier to build wind and solar than it is to build new nuclear at this point in this country. So all those factors combined, again, and this is sort of my opinion and my interpretation of the data. I didn't conduct those models, like the scenarios that I showed earlier, National Renewable Energy Lab, Princeton, they're the ones looking at the cost and the deployment patterns of these technologies. So, I'm kind of falling back on well, that's what the models say, but I think the models are based on lowest cost deployment. Yeah.
Yeah, so I've been in the energy business for a very long time and look at this in detail, a lot. So let me challenge your bottom line that we need a lot more transmission. So I agree, you have to have a lot more renewable electrons, solar and wind from batteries, reach consumers. There's no question about that. That capacity chart, 2 gigawatts, I agree with that. I see 2 problems or 3 problems that we're not attending to and would love your comments. So the way the current incentives are structured, they're structured for people who want to make money to want to go build a giant wind farm or utility scale solar somewhere. Yeah. And they'll find a place where it's cheap. Then they apply to go to an interconnection queue, and that's not at all coordinated where there might be room in the transmission. So that's why that's one of the reasons you got that series of failures and high costs and increasing failures. There's money to be made in solar and wind, and we don't have a comparable set of, so it's very siloed and designed for failure, I would say. One of the remedies to that, I think, is to provide incentives to site these things where there are existing transmission lines and reconductor the, you know, we can increase the capacity of existing transmission lines by putting new wires. Yeah. And we're not doing that. We have, so we don't need to build more transmission in the sense that we don't need more transmission corridors.
Can you let him answer, please?
So that's my question is, would you agree that if we do things right, we don't need to build new transmission corridors, we can just reconduct our existing ones if we have the right policies?
Yeah, and Cheryl, I'll be quick, but yeah, I mean, that was my sub-bullet. I was rushing, so I didn't say reconductor, but we need to make the most out of our existing grid, of course. Let me just also say that wind and solar are, to some degree, I don't want to say geographically constrained, but we can geographically optimize for wind and solar because, look, it's not super windy everywhere in the United States. There are very, very windy places where we're going to generate wind energy at lower cost. So it also makes sense to, from a cost-benefit standpoint, it makes sense to proactively plan and build transmission to those regions where we can generate lowest cost wind and solar. So it's both, yeah, but great point.
I'm sorry, we don't have time now for any more questions, but stay, please listen to all the speakers and we'll have time at the end because we won't be trying to match other rooms. Okay, thank you very much, Joe. And now we're going to move on to our next speaker. Let me introduce our second speaker. Dr. Helena Kazduzian is a Senior Technology Manager for Advanced Materials and Manufacturing Technologies Office at the Department of Energy, DOE, managing a critical materials research, development, and demonstration portfolio, including the Critical Materials Institute. Helena is also the DOE co-chair to the Critical Materials Subcommittee of the National Science and Technology Council, and she coordinates research activities in the DOE's Office of the Undersecretary for Science and Innovation. Before joining DOE, Helena earned her PhD from Iowa State University in wind energy science, engineering, and policy, and spent a few years at Ames National Laboratory evaluating magnetic materials in electric machines using finite element analysis. Let us welcome her as she speaks about the building blocks of renewable energy technologies. Thank you.
Can everyone hear me okay? Okay, great. So I'm excited. I haven't been at an APS conference in quite a few years, and it's my first time at the April meeting, so it's pretty exciting. I'm a generalist these days, so I think my talk will reflect that. I think a lot about the interconnections of different technologies. I'm going to be talking about critical materials, and I'll do a little primer on what that really means. I've been working in this area for about 10 years and really been focused on the lens of them for renewable energy technologies. All right, so what even is a critical material? You probably, if you've heard of critical materials, you might have also heard of critical minerals. They're used pretty interchangeably. And so in 2007, the National Academies actually developed out this methodology to determine what is critical. And so it's based on two factors. The first is supply risk. So is there a likelihood that a disruption will happen in a supply chain and prevent the supply of those minerals or materials to support a particular technology? And then what varies to some extent in the world is the y-axis, which is what happens, who cares if there's a supply disruption? And so when you see the supply, right, it could be a company looking at it. What happens if I'm GE and I can't get, a particular material? Governments look at this, but this general methodology is used all over the world. The U.S. Geological Survey does assessment every couple of years to determine what is a critical mineral. Canada, Australia, the EU, and Japan also have their own lists of what is critical for their economies. So USGS has recently updated their list of what is a critical mineral, and they're really looking at that y-axis, what matters for the entire US economy and national security. So it's a pretty big bucket in terms of why we care about it, and it's about 50 elements on that list, so it's a lot. At DOE, we think about critical materials, and we apply the lens of energy. So we care about what happens if energy technology can't get a particular material. But also in statute, any critical mineral is a critical material. So they are kind of the same in a lot of ways. So our definition is both more narrow and more broad in a sense. And so these materials are really the building blocks of clean energy technologies. And so Joe has done a really good job of doing a lot of work for me on talking about what that transition is going to look like in the United States. But when you look at the elements that are the building blocks of all of these components and these different clean energy technologies, they are elements that have supply risks associated with them. So I'll talk a little bit more about what these look like. And I'll spend most of the time thinking about magnets for wind, which is where I spend most of my time working. But we also have a lot of elements that are used in electrodes for lithium-ion batteries, both energy storage on the grid as well as for electric vehicles. As we're looking to increase the production of green hydrogen and also potentially the use of fuel cells, some of the platinum group metals become important there. Gallium is important for wide bandgap semiconductors used in the power electronics for high voltage power generation, and many of these new clean energy technologies are high voltage transmission technologies. And the gallium arsenide is also used in LEDs for efficient lighting, and I think recently DOE did one of our few regulatory functions is around lighting, and the use of halogen bulbs is being phased out, right? So these technologies underpin some of the goals, right? So Joe mentioned, right, 100% clean electricity generation by 2035. Also, generally, a net zero economy by 2050 is another goal we have as a nation. And so DOE is working towards some near-term goals to deploy more offshore wind, as well as incentivize the adoption of electric vehicles in the transportation sector. And I just want to say, I think this is interesting to think about where the materials come from. Your cell phone has about 2/3 of the periodic table in it. So it is quite complex to think about where all of these things come from, and can you actually get them for your application. So I'll just pull the thread a little bit. What does it actually do in some of these technologies? So in a wind turbine on offshore, we generally use a direct drive generator. And what that means is that the shaft of the generator is going at the same rotational speed as the blades. And so there's no gearbox increasing that rotational speed, and so you need to generate really high torque at low speeds, right? And so permanent magnet machines are very good at that. And neodymium ion boron magnets are used in those machines, and they're the strongest permanent magnets that are available commercially, right? And so the neodymium, the praseodymium are part of that alloy. Dysprosium is used to increase the operating temperature of those magnets. You can look at other configurations. You could put a single stage gearbox in there and shrink the generator a little bit. But gearboxes tend to break down. If you pass a wind farm, you might see one's not spinning. It could be because of curtailment, but it might be waiting for a gearbox repair. And so when you have offshore wind, you don't want to have to repair a gearbox, right? So that's why we prefer this technology. And so as we look to actually deploy these technologies, we literally need tons, thousands of tons of these permanent magnets to make that goal. And where are they going to come from, right? We got to make sure we have access to those materials. So I think that just kind of puts in context the magnitude of the materials that we need to make this transition happen. When we look at electric vehicles, I heard someone say recently, some people think you just plug a battery into an electric vehicle and it goes, but there is a component of the actual traction motor that is a permanent magnet motor, again, using these neodymium ion boron magnets. And also, most of the power functions in your car are probably permanent, a neodymium ion boron magnet. As the price has gone down, the tend to use ferrites is lower. But the other materials that I mentioned, some of these that go into the electrodes are quite more prevalent in terms of the amount of materials we need. It's a lot. So this is a figure that was in a recent ASME Mechanical Engineering magazine showing, for a particular electric vehicle, this is the Mustang Mach-E, the volume or mass of materials that you need for a single electric vehicle. So you accumulate that right to our goals, and it's a lot. So this was a study done recently by the International Energy Agency that shows globally, if we all achieve our goals of net zero economies by 2050, how many minerals do we need? And that's a lot. It's 400 to 600 more percent minerals. So we are really transitioning from a fuel intensity energy economy to a mineral-intensive energy economy as we look to achieve those goals. And the battery critical materials here, lithium in particular, we see the most increase in those demands. And lithium batteries is a pretty new technology. There will be some evolution, but we probably will eventually go to solid state, and that'll take even more lithium than we use right now. So there is the potential for disruptors, but we anticipate a lot of lithium in general. And so the reason this is a challenge is because of the supply chains themselves. So when we look at, I'll use neodymium ion boron magnets as an example. There's two major things, right? When we look at the concentration of the capabilities globally, they tend to be just in one or two countries. And so that's a single point of failure if one country is no longer able to produce, right? And there's also some geopolitical considerations when we look at these particular countries. Additionally, it's the lack of the midstream capability. So what I mean by that is the ability to actually process and refine these materials once they're out of the ground. And so we look at at this particular example, the inner ring here is mining in the world. So the U.S. is actually the second largest miner of rare earth elements. But we don't have the capability to actually refine those materials. So we export those materials, they get refined, they get put into components, and then we import them in the form of value-add components. So that's a huge lost opportunity in terms of economic value. Manufacturing is really where the dollars are generated for the economy. And it also just put us at risk, right? How are we actually going to get the components we need to build these wind turbines, for example? And it's the same thing if we look at recycling. We still need that capacity to refine those materials once they're extracted from those particular end-of-life components. And so that's one example, but it's very similar across many of these different material classes. Last year, the Department of Energy did fund some deep dive assessments of different material and actual end-use technologies like nuclear, photovoltaic, and wind. But I'll highlight here energy storage, magnets, platinum group metals, and semiconductors as ones that touch on critical materials and show a very similar story where we don't have that midstream refining capacity, and that puts us at risk to achieve our goals. So what do we do about it? This is a huge challenge that many countries are working on. And the whole federal government does work together in this role. One of my goals, or one of my hats that I wear in this area is to help coordinate the work that we do across the federal government. But DOE is really focused on the research. And recently, the Energy Act of 2020 did expand our ability to work on this. We had focused more on basic science and applied R&D. Now we can also think about large demonstration and actual commercialization of these technologies to kind of enhance what we're doing. And we work with other agencies on some of these topics. I'm not going to dwell on those, but happy to talk about them with anyone afterwards. So our strategy around here, our vision is really to make sure that we have resilient supply chains to meet the clean energy transition. We want to support, the clean energy transition to decarbonize our economy. We want to do that in a responsible way. And we also want to think about multiple timescales, right? We need to meet the moment and mitigate climate change, but those needs won't disappear. If we meet 2035, 2030 goals, we're going to continue to need to deploy energy. We're going to continue to need to get materials to do that. And so we need to innovate and think about how to do this better in the future, right? We have to work with what we have now, but that's not going to get us there in the long term. So I think it's really important for us to continue to do that basic science and applied R&D work. And so when we look at all those different types of research, we think about them in these different pillars. So can we actually make sure we have availability of supply? So diversifying the sources that we use, but also looking at expanding the sources. So for example, coal mining is going away. There's all this mine waste from coal mining, and they contain really low concentrations of a lot of these materials. So can we transform those waste piles into a resource and also remediate those waste piles, as well as providing economic opportunity for folks, because people right now in those communities have good jobs, right? Union paying jobs, often working on coal plants. So we need to think about the transition for those communities in particular. Looking at alternatives, right? Can we just not use these materials, right? That could be like looking at new magnet compositions. It can also be completely technology substitution, but reduce our reliance in general and look at more available materials. Thinking about the efficiency of the use of those materials, right? At every stage of supply chain, are we getting a good yield? Are we thinking about all of the different life cycle inputs in a way that we're reducing chemical intensity, water intensity? Can we extend the lifetime of materials, right? Not just recycling, but remanufacturing, refurbishing, thinking about designing with that in mind. We can basically, offset the need for some virgin demand, but because the demand is growing so high, I think we can't recycle our way out of this, unfortunately. And then we do a lot of other things too, like assessing what is critical, looking at life cycle assessment, developing international standards. So there's a lot of activities that go into supporting this, and of course it's all underpinned by education, workforce development. It takes people to do this. And it's not just the higher education degrees, it's also the technicians and teachers to make this happen. We recently did put out a new website on this, so if you're interested in kind of staying up with what DOS is doing, please take a look. Where it's just really a soft phase, and we'll be updating it hopefully at the end of May. All right, so what does this look like in implementation, right? We have this, it's a mouthful, but it's basically a research program that spans basic science to commercialization and thinks about these different pillars to actually make this happen. We get money every year that we spend on this, but we actually got some additional, money to do this with the Energy Act of 2020, and I'll talk more about some of the other things that we do. This is just like a sample of some of the things we do, right? So looking at basic science, we have, material science, separation science, geoscience, looking at some public-private partnerships that I'll touch on, and then also looking at financing of actual processing facilities, as well as some commercialization activity that we have going on. There's 17 offices in DOE that work in this area, so I can't give justice to everything that we do, but I'll touch on a couple things. So in the near term, right, we need to actually build supply chains and provide solutions. And so the bipartisan infrastructure law provided over $9 billion that are specific to critical materials. This isn't everything that's there. My slides are always busy. I tried to make them a little less busy. But you can see that we have $600 million specifically for this program. And that's not all we'll spend on the program, but it is something that's specific for it. Looking at actually building facilities. So this particular rare element demonstration facility is the way to prove out the extraction of those elements from coal and other deleterious materials. $6 billion for batteries, which is a ton, right? So we're in on there, and I'll talk more about that. And then also hydrogen, right? That is one way for us. I think we pale in comparison to what the EU is doing, but it is a start. And then I think looking at what we've done recently, so that's like things that we've gotten, but things that are actually going out the door. About half of them, that $6 billion for batteries has gone out the door to build actually, commercial facilities to actually process and manufacture, recycle. Additional money to advance recycling and reuse technologies, looking at long duration storage, so not just batteries for EVs, but also looking at flow batteries and other alternative technologies for the grid. And then our loan program office has actually put out some conditional awards to actually build some more production capacity for battery materials. ARPA-E has been leading the way on kind of mining of the future research. So can we do this in a different way and also actually use it as a carbon sink so we can be part of that solution for decarbonization. Lots of things that we're up to. And then the Inflation Reduction Act is actually looking to provide tax credits to incentivize the production of these materials and use domestic materials and end-use technologies. So industrial policy is often a four-letter word in the United States, so it's kind of, I think, exciting to see some of these policy incentives to build our supply chains. So that's in the near term. In the long term, we need to innovate. We need to, some of the technologies to process materials are decades old, and we can do them better. So we look at different ways to do that. And so in our Office of Science, in the Basic Energy Sciences office, they're looking at separation science. And so what that really is looking at is, how can you get these separated out of really dilute species, and also at the intermolecular interactions. The rare earth elements, the lanthanides, right, they're very similar, and to separate adjacent lanthanides is difficult. So that's kind of like, and then if they're in like a coal, waste, they're very dilute. So that's kind of like some of the hardest work I think that we fund. And they're looking at different modes of energy transfer to actually separate those out. This is just a quick example of some of those techniques, looking at those different modes of energy transfer, right? Electrochemical approaches, looking at bio-based approaches. So lignmodulin is a protein that's been explored quite extensively for rare earth element separation, and actually DARPA is like blowing up the research in this area quite a bit in one of their programs now. Looking at enhanced separation of lanthanides with magnetic field simulation, like so, basically taking advantage of the different structure, the different coordination chemistry, and then also supramolecular chemistry. I'm not a chemist, so I'm not going to do justice to that, but it is pretty cool what they're doing there. We also have, I mentioned, a lot of public-private partnerships that look to advance this. So the Critical Materials Institute is in my program personally at DOE. It was founded in 2010. It's led by Ames National Lab. It's a consortium of 4 national labs, about a dozen universities, and 30 companies-ish that are all working together to look at this issue. It was founded right after our first DOE critical material strategy. So it's, the focus areas of the research are directly connected to that initial strategy. And so if we look at that, that supply chain and where the gaps are, a lot of different technology and science solutions to address some of those gaps and do things better. So some of it's looking at ways to just improve what industry uses. So when we look at mined ore, you have to concentrate that ore to get the most out of it. So looking at design of novel flotation collectors and improve their recovery, and that, again, the goal is that if you were to incorporate that into the world, you would improve not just the yield, but also reduce the costs. Getting rid of caustic cracking and leaching. Caustic cracking is used because of the fact that the rare earth elements ends up in a fluoride configuration, and it does limit the actual efficiency of the recovery. So rather than using that, they use, I'm forgetting exactly the step here, but it's a one-step hydrochloric leach and improves the recovery to 70% or 90% from 70% what would be usually achieved. This is where some of the more fundamental work comes in, at looking at the design of ligands themselves, assisted with AI and machine learning approaches. And this was actually supported and put into the world, right? We actually designed and synthesized these ligands and improved the adjacent lanthanide separation factor from about 2.5 to 6.7, which is a pretty big deal. And Marshall Technologies is right now piloting this. They're a chemical producer, so the idea is that they would actually produce these domestically. Also looking at the other side of things, at recycling, we focus our efforts right now on electronic waste because that's where things are. Eventually, we'll have more things in circulation as offshore wind turbines, get decommissioned. But right now, we don't have a lot of that, right? So hard disk drives in particular are some where permanent magnets can be found in somewhat concentrations. They're also, in your earbuds and your cell phones, but very, very good source. So there's two different technologies here. One is using copper salts that actually just selectively leaches out the rare earth elements and leaves the rest of the e-waste intact. And that's really important because e-waste recycling is already an industry on its own, right? So you can basically add a little loop, a circular loop to it, and it's a little bit copper enriched, which is good for the folks who are thinking about copper recovery. And then membrane solvent extraction is pretty interesting too, because if you look at conventional solvent extraction, it's hundreds of stages of mixers and settlers in industry. And this is just, a modular system that you could bring to a recycler. You can just keep regenerating or reintroducing the aqueous phase into the membrane and just keep getting the material out, and so you don't have to build many, many, many stages of solvent extraction mixer settlers. They also were able to tailor the extractants in this system, so they could actually focus one system on battery materials, as well as this one is focused on electric or rare earth elements. Both of these actually got picked up with partners in industry and are building pilots right now. This one is in a pilot stage. This one actually got some additional funding through that bipartisan infrastructure law. And the building battery recycling plants. So it's pretty exciting to see this actually getting into the world. We've been doing this for a decade now, so it's, it seems like a long time, but when you think about how long it takes to take a novel idea to the world, it's pretty fast. And then finally, I'll touch on some of the work that we do to get these materials out of coal sources. So this is the CORE CM initiative, the Carbon Ore Rare Earth Critical Minerals Initiative is what that stands for. And they're looking to characterize these coal basins across the country. These are really regional initiatives, partnerships between labs, industry, and academia. And give a sense of some of the things they're doing. There's a education aspect of that, and it's not just the characterization; it's also the development of the technologies to get these materials out of the earth. And so, and in parallel, they've been looking at this technology for a long time. So they have actually 4 small pilot facilities that are currently running, seeing if this works for different coal sources. So coal waste comes in quite a few different forms. And so I'll just go to this next one. This one is looking at acid mine drainage. And it's kind of interesting because you can just put this directly into a solvent extraction system. You can use conventional technologies to do it fast. And they've had really good success. They're getting out the mixed rare earth oxides at a high purity. And then the idea, right, some of that separation technology would come into play next, right? Because there's not a neodymium ore, unfortunately. Most of the rare elements are in any particular source or any mineral, so you have to really get the ones out that you want the most. So I know I'm a fast talker, that's a ton of information. I hope it was interesting to you all. If you're interested, again, we do have this new website. If you Google or just go to energy.gov/critical materials or critical minerals, it'll take you there. If you're interested in understanding what we think is critical, we're actually going to be publishing an update to our assessment in end of May. So May 31st is when that'll hit, and we'll have that open for public comment. So if this is something that you're interested in, please take a look. And then this is a little bit more of my office. We just recently become a new office. We were formerly the manufacturing office. So if you want to take a look at what we're doing, these slides, I can make them available. I think they'll be on the APS portal. So thanks so much.
Questions. We have 5 minutes for questions for the speaker.
Hi, thanks for a really comprehensive and interesting talk. I have a question that's kind of maybe a side issue, though it was mentioned in one of your slides, and that was about hydrogen for mostly, I suppose, for portable or transportation. But you talked about electrolysis, but that, of course, uses electricity, and that has to be generated by some other means. I wondered if I've heard something about using photoprocesses and sunlight as an experimental way to move in the direction of producing hydrogen without using up electricity, which could otherwise be used for the electrical economy. Could you comment on that?
So I am not personally an expert on hydrogen, but we do have, I think, an energy earthshot on hydrogen. So I think that would be something to take a look at.
So in one of your earlier slides about the supply chain, there is a salient feature where you show the different countries, this onion
The
thing.
donut,
Okay,
yeah.
so there is one country which by far dominates
Yes.
this slide, and there were no comments on that. So I do not want to sound antagonistic, on the contrary. I'm just wondering, though, a story we've been hearing until recently was that China was building more coal-fired plants, right? Suddenly now I see this. So I'm wondering, do we understand what went so well in China in this respect and went so wrong here? Do we understand this, as a learning process?
Yeah, so I can use rare earth elements as an example. In the 80s, actually, the United States was self-sufficient in the production of these materials. The Mountain Pass mine in California was operational, and we had Magnequench and some other companies that produced magnets. Magnets, I think, didn't have quite as big of a market as I did now. But that company was, the market. I'm not an economist, but I mean, really, I think the market works the way the market works, and it was cheaper to do this in China. They were very strategic. I think, yeah, some of the capacity left from here. So Magnequench did go to China. It was bought out by a Chinese company. In addition, I think, yeah. So and I can't remember who was the president at the time, but they basically said, like, rare earth elements is going to be our oil. Like, they were very strategic and recognizing that they have a lot of this material. They also have one of the deposits they have is ionic clays, and they have really high concentrations of heavy rare earths, so dysprosium in particular, which we do not have good deposits of in like bastnäsite ore, for example. And so there's some advantages in terms of the resources they have, but they're also importing rare earth elements these days. It's pretty opaque in general what's going on, but we do know that much. And so I think it was an intentional move, right, by the government to invest in the resources they have to produce out the capacity. And kind of before looking, there's also a difference in the way that their government works, right? It's most state-operated facilities or owned facilities. So they've intentionally consolidated that production into a couple of those over time. And I think they made a similar move with battery critical materials. There's the processing capacity they've built out over time, and then additional investments in Africa in particular to get security to those different materials. Cobalt, being mostly found in the DRC in particular. So I think there's been, that would be, my knowledge of that area. I think it's a combination of the market moving things where it's cheaper to produce is when we don't actually capture the cost of what it takes to clean up things at the end of life in our current economy globally, and also just a really intentional move by the government in China to transform their manufacturing sector.
Okay, there's a short question, please, the last one.
Yes, I was just wondering, in historically, energy production tends to harm marginalized communities more, and I'm wondering how that factors into this next step, how environmental justice plays a role.
Yeah, so what I didn't touch on is other goals in the administration beyond just the clean energy targets, and one of those is called Justice 40, and the idea is that 40% of federal investments should benefit disadvantaged communities. That's a very location-based definition in the current administration, and so we're still wrestling what that looks like for different things, right? When it comes to commercialization, it's a little more clear how you could work with communities. When it comes to early stage research, I think we're still trying to figure out the right balance, right? Not just thinking about diversity, equity, inclusion, and teams, but also thinking about the communities themselves. And when is the right time to engage as a scientist or an engineer with the community? Because you don't want to come in with false, expectations that this project is definitely going to come to your community. But I'm in the manufacturing office, and we always talk about, well, how can we make manufacturing something that people are excited to have in their community? I come from rural upstate New York, where we once had manufacturing, and when it left, the community was really devastated, right? So it is a good economic generator, but it can result in people being located near, harmful emissions. So I think that's why a lot of the research that we do in the Critical Materials Institute, we do techno-economic analysis and life cycle assessments really early. We're not working on anything outside the lab in CMI. And it's not necessarily like a go, no go of the research, but it does give us an indication of where we could lower the impacts and where we can also lower the costs. So I think in general, that's the philosophy that I try to bring to my particular program.
Okay, thank you very much. Okay, our last speaker, Paula Garcia, is a senior energy analyst and energy justice lead at the Union of Concerned Scientists. She evaluates energy resources and climate solutions in the electricity sector and works to further public understanding of clean energy technologies, policies, and markets. Paula is committed to advancing energy justice and sustainable development through her work. Ms. Garcia has broad experience as a researcher and analyst, interacting with a variety of stakeholders, including government, community-based organizations, private sector, and international non-governmental organizations. She holds an MA in Sustainable International Development from Brandeis University and an industrial engineering degree from the Javeriana University of Columbia, where she is originally from. She serves on the Boston Area Solar Energy Association's Board of Directors. Let's welcome Paula. She's going to talk on the road to 100% renewables. States can lead an equitable energy transition. Thank you.
Thank you so much, Sherry. So, yes, I'm Paula Garcia. I use she, her, ella pronouns, and I work with the Union of Concerned Scientists, or UCS. UCS is an organization that was created more than 50 years ago in 1969 by a group of scientists and students that wanted to make sure that science was being used to address the most pressing environmental and social problems. Our organization works in different areas, including nuclear safety, climate and energy, clean transportation, food and environment, and we have the Center for Science and Democracy. So it's been great to hear from Joe and Elena. Thank you so much for setting the context of where we are right now and the different challenges and opportunities, more importantly, that we have ahead. As Joe was mentioning, the question about this clean energy transition is not so much about the technical or economic aspects of the transition, but more about the procedural, institutional, and social components of the transition. And as Elena mentioned, research on critical materials or transition minerals is also really important to ensure that we're going to be able to have a successful transition to renewable energy. In my presentation today, I'm going to explore further what it's what this transition to clean energy can look like on the ground. And for that purpose, I'm going to be sharing key insights from the On the Road to 100% Renewable analysis. This analysis was conducted. I was the lead analyst for this study, and it was conducted in collaboration with 3 environmental justice organizations, COPAL in Minnesota, Green Roots in Massachusetts, and the Michigan Environmental Justice Coalition. And basically what we wanted to make sure is that by having this collaboration, our scenarios and the outputs from the analysis we're going to be communicating what this transition could mean at local level. So from the get-go, we wanted to center people in the analysis. And what I mean by centering people is that we wanted to identify how our energy choices impact people's everyday life. So as a brief overview of the analysis, we wanted to see how leadership states can address climate change by reducing heat trapping emissions in the electricity sector. So that's an important piece of context. This analysis was not economy-wide, was focused on the electricity sector. So we look at 24 states that are members of the United States Climate Alliance. These states is a coalition of governors that have committed to advance the commitments of the Paris Climate Agreement. And the electricity sector has a key role in decarbonizing the grid as we are electrifying other sectors of the economy like transportation and buildings. So basically what we did in our analysis is that we look at the implications of these states meeting 100% of their electricity needs by 2035 through a renewable electricity standard, or RES. And Joe gave like a lot of information on the different efforts that have happened on that front. This level of ambition, as you already also heard, is aligned with the Biden administration efforts to make electricity generation carbon-free by 2035, and also resonates with a growing number of states that are already committing to 100%, being Minnesota one of the last states that joined these efforts, but also resonates with other cities, towns, and companies that are moving in that direction. In terms of the modeling, we use the Regional Energy Deployment System Electricity Model, or REIT, from the National Renewable Energy Laboratory. This model helps us to project changes in energy capacity and generation, changes in CO2, sulfur dioxide, nitrogen oxide emissions, and also implications in terms of capital investment. And we also collaborated with GreenLink Analytics to be able to understand those everyday impacts like health, changes in jobs, and also energy burden. In our analysis, we included 5 different scenarios. The first one, no new policy, basically electricity sector policies that states had in place by July 2021, including state renewable electricity or clean electricity standards, as well as federal tax credits. This means that at that moment, the Inflation Reduction Act was not already in place, so that was not integrated into our analysis, which means that the benefits on the economic side could be even higher. That's one thing that I want to make sure that we are all on the same page. Then the main policy scenario that we included in our analysis is the 100% renewable electricity standard, or RES. Basically, each state committing to meet 100% of their electricity needs with renewable energy by 2035. But we also included a 56% increase in electricity demand by 2040, recognizing that we need to start electrifying transportation and heating. Then, one quick question. In your states, what sector is the one that is generating the most CO2 emission? Can you please raise your hand? Transportation? Buildings? Electricity? So I live in Massachusetts, and the debate right now is going in the direction of the sectors in Massachusetts that are generating the most CO2 emissions are transportation and buildings. Let's focus our attention in those sectors, and the grid, let's put on hold the action on the grid. So basically what we wanted to check with this scenario was like, okay, what if all the energy goes to address transportation and buildings and we do not invest in decarbonizing our electricity sector? And then for Massachusetts, Michigan, and Minnesota, we had a fourth scenario, basically constraining the development of new gas-fueled power plants after 2025, and also accelerating the retirement of coal plants by 2030. And finally, we also had a fifth scenario looking at a clean electricity standard. Basically, the difference between a renewable electricity standard and a clean energy standard are the technologies that you allow to classify to fulfill the requirement. In a clean electricity standard, you can also include nuclear power and carbon capture and storage. So in terms of the results, the first one is that climate aligned states can meet 100% of their electricity consumption with renewable energy by 2035. And this holds true even as we are increasing the demand in electricity due to the electrification of transportation and heating. So again, US climate aligned states can meet 100% of their electricity with renewables by 2035. It's technically feasible. And the graph on the left is showing us the results for the no-new policy scenario, basically business as usual. The graph on the right is showing us what will be the picture in terms of moving to 100% RES. And what you can see is that solar generation in these states grows nearly 9-fold, is the yellow in the graph, and wind generation more than 7-fold is the light blue. You can also see that coal basically disappears by the year 2040, but you can also see that by 2040, electricity generation in these states is 73% renewable. And it is not 100% because a renewable electricity standard is about consumption, not generation. So all of the US climate aligned states meet the requirement of the renewable electricity standard. And that translates in a 73% of renewable energy. And our model allows other sources like coal and gas and nuclear to continue operating, which they do because the principal US grid is interconnected and power is allowed to be shared across the state lines. So a transition to 100% renewables is about more than just the technology. It is also about the benefits in terms of health, climate, economies, and energy affordability. For example, accelerating the deployment of renewable energy creates new opportunities in the installation of solar arrays, wind facilities. There is a lot happening on offshore wind. We have this 30 gigawatts target already in place. There is a lot of different projects, procurements that are happening in the East Coast, in the West Coast, in the Southeast, and in the Middle West. And in Minnesota alone, our 100% RES policy creates more than 40,000 additional jobs from 2022 through 2040. And you can see in the slide additional economic benefits in terms of labor income and gross domestic product. Now, this transition to 100% renewables is needed. And look, what the shift to 100% RES policy also reduces the amount of harmful air pollution from power plants much more than in our no new policy scenario or business as usual. So on the left, we have the results for sulfur dioxide. On the right, we have the results for nitrogen oxides. The blue line is the no-new policy scenario. The red line is our 100% RES scenario. And for sulfur dioxide, emissions from power plants in the US Climate Alliance states falls 88% by 2040, compared to 27% under current policies and plans. And for nitrogen oxides, emissions fall 77% compared with only 18% under our business as usual case. And this move leads to approximately between 6,000 and 13,000 fewer premature deaths, more than 140,000 fewer cases of asthma exacerbation, 700,000 fewer work days that are being lost due to illness, and also a value of public health benefits of more than 280 billion over the 2 decades. And something that most of us are familiar with, a transition to clean energy helps us to address the climate crisis, help us to decrease CO2 emissions, help us to clean up the power grid in a significant way. So the blue line, business as usual, red line, our 100% RES scenario, yellow line, the electrification without decarbonization scenario. What you can see is that the reduction of fossil fuel use in our 100% RES policy translates into almost 60% reduction in CO2 emissions between 2020 and 2040. If we were to keep on doing things as we are doing them right now, the current policies and plans that we have in place, the reduction is only going to be 10%. And just a few weeks ago, we have the results from the IPCC saying that we need to take decisive action in this decade to make sure that global temperature is not going to increase more than 1.5 degrees Celsius. The other thing that is important also, going back to the scenario of like, let's focus on the sectors that are polluting the most. Let's put all the attention on transportation and buildings. Let's put on hold taking action on the grid. What you can see is that the results for that electrification without decarbonization scenario, the yellow line, we get plant emissions that are nearly 5 times higher for sulfur dioxide, more than 3 times higher for nitrogen oxides, and more than twice as high for CO2 by 2040 compared to our key policy case, which is the 100% RES scenario. And even the emissions for that electrification without decarbonization scenario would be 14% higher than just keep on doing current policies and plans that we have in place. So in terms of recommendations from our analysis, we have a range of policies building on the renewable electricity standard to make sure that we are quickly moving away from fossil fuels, that we are reducing pollution, and that we promote an equitable outcome in the transition to renewable energy. Some of these include, first of all, targeting reductions in power plant pollution. Globally, more than 8 million people died in 2018 due to air pollution from burning coal, diesel, and other fossil fuels. So this is why it's so important to targeting those reductions in power plant pollution particularly. We also need to promote a just transition for fossil fuel workers and frontline communities. Elena touched on that piece. We're talking about the livelihood of people right here. So as we are moving away from fossil fuels to renewables, we need to make sure that people that depend on the fossil fuel industry can thrive in the long run. We also need to direct investments in communities to increase clean energy and reduce the energy burden. So just for context, the energy burden is the percentage of the income of a household that needs to be spent to cover the energy part of their bills. And it is particularly a challenge for many lower income households. Their national energy burden for electricity and gas alone is 8.1%, compared with an average of only 2.3% for non-low income households. So the direct investment in things like energy efficiency and rooftop solar could be a very important piece in helping these households to reduce their electricity bills as well. The other piece that is very important is to develop a workforce programs and entrepreneurship initiatives in renewable energy to foster high quality, good paying jobs. Solar Foundation report from 2019 found that women represented only 26% of the solar workforce in 2018, Hispanic or Latino workers only 17%, Asian workers 9%, and Black or African American workers only 8%. And if you were to look at leadership, those numbers were even smaller. So Black, brown, indigenous, immigrant, and low-income communities should have full access to the new jobs, economic development, and entrepreneurship initiatives that this transition to clean energy can yield. Also, we need to ensure that frontline communities have power in decision-making, especially connected with all the siting and permitting processes, mining of transition minerals, those projects that will be directly impacting them, those communities need to be at the table participating in how the decisions are being made. And that touches on something that Joe was also mentioning. And there are studies that are showing that actually that kind of engagement in the long run are helping projects to move forward instead of a position of, we are going to be doing this and you just take it if you like it or not, and then they will hold the opposition and pushback that happens that delays actually projects much more. And super important, we need to enable this transition, so we need to target transmission additions and non-wires alternatives like distributed generation, flexible demand, aggregation of those distributed energy resources, reducing the reliance on urban-based fossil fuel plants. And we need to ensure a responsible life cycle for clean energy technologies. And of course, state action is super important, just as important as supporting strong federal policies. If you want to learn more about the recommendations or the methodologies of the methodology of the analysis, it is online on the road to renewables, on the road to 100% renewables. There are blogs and there are fact sheets and there is a webinar, so please go online. Thank you so much.
We have quite a few minutes for questions for Paula or any of the other speakers, if you have. Those of you who I cut off earlier.
Yeah, I do have a question. You said that those activities would generate 40,000 jobs here in Minnesota, which seems perfectly sensible. But then you also said in the same slide that would be 49 billion in labor income, which would mean more than $1 million per job. Is that a typo or what?
Let me go back.
Or maybe I misread it, I don't know.
This one?
Yeah, 4.9, oh, okay. That's like over $100,000
It's
per
20
job.
years.
That
Yes.
seems a little high, isn't it?
It's cumulative from 2020 through 2022 through 2040.
That makes sense. Okay.
So you're a collective of states that are doing this. I don't remember, it obviously includes a majority of the citizens or the population of the United States, but it's not everybody. I happen to live in Montana, which is a bit of a disaster. And I'm just curious, what the challenges are to getting more of the states on board for this agenda, and what a difference it would make. Or should we be happy with I think it's 25 jurisdictions, if I counted them, that are on board?
Yeah, thank you so much for that question. So the entry point for our analysis was to focus on the US climate alliance states because of the commitment that the governors have made to advance the Paris Climate Agreement. But that was not to say that other states should not be taking action, first of all. There are different challenges, as like one of the things that Joe was mentioning, the policy piece of it and the political piece of it is a huge one. I do strongly believe that if people can see themselves in the transition, if they can like understand what the benefits what benefits are there for them in terms of clean energy transition, then you're going to have more buy-in. I also think that's important, general education for people to understand the possibilities and opportunities of clean energy. There is a lot of disinformation out there. We still keep on hearing that it's expensive, which is not true at this point. We keep on hearing that it's not reliable, which is not true at this point. So we need to work more in public education in terms of what's been the progress, where we are at, what are the opportunities, and we need public engagement in terms of people asking their legislators, this is important to me, you're representing me, make sure that you're putting the right policies in place.
Well, thank you for your presentation. I think when I talk to industry, I think there's a broad recognition that we need a social license to operate, right, for the transition minerals that you mentioned. And getting communities to the table is a really powerful way to get that. Are there any particular models or examples of ways that that's been done effectively? Because I find that generally when I ask that question, that there is none in the United States. So I'm just curious if there's any examples that you could provide that would be a good model.
Okay, that's an awesome question as well. So I'm with you. It's not an easy task. One of the technologies in which I focus on is offshore wind, and I don't know if you're aware of the moratorium that indigenous peoples are requesting from the government in terms of advancing the plans on deployment of offshore wind. That talks about the lack of proper engagement that those of us have been putting in place in terms of the engagement with indigenous peoples. We need to be creative, we need to be innovative. There are specific places where the conversation is changing. Like in New Jersey, there is this law that was passed, I don't know, like 2019, 2020, that's like on cumulative impacts and engagement with environmental justice communities. So that's changing the conversation, and that's making that developers and the state and the regulators are having to make that extra effort for engagement instead of like, we need to streamline things here. We don't have time to stop and try to find a good process for engagement. It's by law is being required, and that's changing the dynamic. And there are similar efforts happening elsewhere, like in Massachusetts. That's one of the key priorities that it's happening in the energy arena in terms of siting reform to make sure that the same people that have suffered from the disproportionate concentration of fossil fuel plants that have affected their livelihood are not the ones that will keep on suffering from other kind of energy infrastructure that maybe they don't want in their neighborhood because they have already been overburdened. And it's like, if you're going to be putting a huge energy storage facility in an environmental justice neighborhood, in a place where there was a playground that the community wanted to see instead of the storage facility, is there a better place to locate that storage facility? That's the conversation, cumulative impacts and how to make sure that we don't keep on overburdening the same communities, and how we make sure that there is better engagement to find alternatives that get more consensus.
So I wanted to ask a question which will take the discussion for a moment in another direction. I wanted to go back to the question about nuclear power.
Yes.
And maybe Joe or maybe Helen or someone else can address this, so I'm kind of opening it up. But my understanding is that, as Joe said, the costs are quite high in the United States, and that's one of the main impediments, and various other problems. But in other parts of the world, that's not been the case. And I'm thinking in particular of Sweden, where because of the oil crisis that happened in the early 1970s, the government and the population made a commitment to go 100% nuclear. And within 10 years, almost all the electricity was nuclear. So if my understanding of that is at all correct, that's an example where it shows that if the society understands and makes a commitment, and they haven't had any significant accidents in Sweden, and Finland has also made a commitment, not so much for itself, but it's selling nuclear power electricity to other nuclear power generated electricity to other countries in Europe. So I just want to raise the question whether, is there something that we can do in the United States that could remove the barriers to this kind of, it would be a huge diminishment in carbon if we move to really a huge concentration of nuclear generated electricity, and for electric vehicles too. So.
Yeah, that's a great question, and I think that we all have something to say here. I think that one of the biggest problems right now is not so much about existing nuclear plants in the United States that are operating within some sort of boundaries on the safe kind of spectrum. I think that the problem is right now about new nuclear power plants, and the few projects that have been happening have been overpriced. So if you look at the cost proposition, it's not a good one for nuclear at this point. And then you have the safety discussion around small modular reactors, which is a different kind of discussion.
I'll just add one comment. I'm sure Joe has some maybe actually answers for you, but I think when you look at the difference in risk perception at the Americans versus other countries, I'll use France as an example. They have a really high deployment of nuclear energy in France as well, and there's a larger trust in institutions in general and in their government's capability in that society versus American society. And this study was done before some of the more recent current events in our country. So I think one challenge is that social license, and combating that misinformation is challenging. So it is generally Americans don't have good faith in the government or in institutions in general. Science is a little bit better than media or some of these bigger institutions, but in general, if you compare it to countries like France, it's just lower faith. So that's a barrier, I guess.
Yeah, and just a couple other additions. I mean, I do agree with what you know, both the other presenters said, but just I guess as an anecdote to kind of understand the landscape in the United States, we actually just had a new nuclear power plant come online in Georgia like last week. It was supposed to cost $14 billion and it cost $35 billion. So I'm not saying we can't or shouldn't continue to deploy nuclear, but it's risky on multiple perspectives. Namely, the cost is risky. So for us as ratepayers, you know, I don't want to be paying that massive cost overrun for a nuclear power plant when we know that we can quickly, rapidly, and at very low cost deploy other sources of electricity. Again, I want to stress that, you know, we have 20% of our electricity coming from nuclear already. I think that's excellent. Do we need to get 100% nuclear? No, we have a lot of options. We need a broad portfolio of electricity sources that are low carbon or zero carbon. Nuclear should play in that mix, but do we need to rapidly ramp it up?
Why is the cost so high in the US that's not so high in these other countries? France, particularly in Sweden, in Finland?
Yeah, I mean, I don't actually know the answer to that. Maybe it plays into what some of the others were saying, but
I do, actually.
Oh, okay, yeah.
Go ahead. I mean, I'm not at all an expert on this, but I'm French. And you know all that right now in Europe, it's a bit of a crisis concerning the energy and energy production. And right now, producing electricity through nuclear production is actually not cost effective anymore. It was true 20 years ago, but now it's exactly what you said. It's just the safety norms have increased so much because of past catastrophes, like, for example, in 2011. You know, everything starts to just build up, like everything is more expensive. And then it's exactly also what you said, the new generation of nuclear power plants are like super expensive. We are like 3-4 times the original cost. And we are like so behind, like 15 years behind the schedule. So I don't know for Sweden, but for France, at least I can answer, this is not the case anymore. So the US actually, I don't think is behind the other countries. Maybe, I mean, and I'm not sure you said behind, but maybe it was true like 20 years ago where actually the prices were much cheaper in Europe, but I don't think this is the case today. Thank you. Here you go.
Hi, I have a comment and then a possibly related question for the first speaker. The comment is that if you saw that slide that's up there right now and it didn't have the label, you might think this is a picture of states with Democratic governors, and the white would be the states with Republican governors. It's maybe not 100%, but it's pretty darn close. And so my question for the first speaker is that you talked about the economics in terms of what is cheapest. But another aspect of the economics is who makes the money and who already has investments that they are trying to protect. And I think most of the opposition to renewable energy is funded by the fossil fuel industry, and that is extremely influential and perhaps might be affecting which states have which types of governors. So I wonder if you could comment, and just, you know, an anecdote is that if you drive through Pennsylvania, which I do fairly often living in Maryland and visiting family, you see billboards that, that don't make sense to a scientist, but they say, the sun goes down, the wind stops blowing, support clean coal. And somebody's paying for those billboards, and people are, you know, people see that, and that's the opposition. So I wondered if you could comment on that aspect of the economics of renewable energies.
Yeah, no, that's a big question, and yeah, I bet the others can speak to it too. I guess, you know, first I should say I'm going to speak my opinion and not that of Lawrence Berkeley Lab or the government. But I also want to say that, you know, I don't really want to speak to whether opposition to wind and solar is true grassroots or whether it's AstroTurf, you know, funded by the fossil fuel industry. I don't really know. I'm sure it's a mix of both. There is research going into that. But what I do want to say is if you were to map where we have installed wind and solar in the United States on a county level map and overlay those counties with who voted Republican or Democrat, you would see that the vast majority of investments to date in clean energy are going to red counties. So the economic benefit, and I'm talking about land lease payments, tax benefits that go to the county level, jobs, a lot of these economic benefits are indeed going to red counties and not blue counties. Not exclusively, it's definitely spread out to both. But also at the same time, and I kind of mentioned this on one of my slides, the vast majority of the economic benefit is going to private investors, and it's not going to those local hosting communities. So there are, like I said, land lease payments, tax payments to the local communities, tax payments to states, and jobs, and other kind of local economic benefits. But when you think about these private companies building, capital-intensive projects, profits are often leaving those communities, right? So can we think about kind of rebalancing that equation a little bit so that maybe a little bit more of the profit or just kind of benefits broadly are staying local in those communities? That might sort of change that paradigm. Anyone else?
I'll just add one little, the Lithium Valley Commission in California is an interesting case study of the state coming together with the geothermal power industry, indigenous communities, the local community in Imperial Valley at the Salton Sea. I'm not saying it's perfect. There's been a study recently that shows maybe some of the ways to improve that. But it could just be an interesting example to take a look at to see how all of those things kind of fit together and a potential regional model of how we might think about these issues in the future.
Okay, I'd like us to thank all our speakers again.